So in this video, we're going to go over heating and cooling curves. So make sure you have out your practice packet. So this is page 9. And make sure you can pause the video and follow along and that you have all of these notes in your packet. Okay, so heating and cooling curves are graphical representations that show how the temperature of a substance will change as heat is either added or removed. So all substances can have their own specific heating or cooling curve. So this first one is a heating curve. Notice how it looks like an upwards staircase. And your cooling curve is going to be the opposite. So it's going to be a downward staircase. So first, let's go over the heating curve. So heating curve is going to represent endothermic processes in which energy is going to be absorbed. So on the x-axis on the bottom, you have time. It could be in minutes or seconds or hours. Sometimes it can be represented as heat absorbed. And on the y-axis, you have temperature. So again, temperature is the average kinetic energy of particles in a substance. So the lower the temperature is, the less the average kinetic energy is, the less motion those particles have. And as you increase that temperature, the more kinetic energy some substance has. Okay, so all of these increasing lines, so this, what I have highlighted in red right now, A to B, C to D, and E to F, these increasing lines or line segments represent the three phases of matter. Okay, so A to B represents a solid. C to D will represent a liquid. And E to F will represent a gas. So essentially, the farther and farther away those particles will get from each other in a substance as kinetic energy or the temperature is increasing. Okay. So what are these blue segments, these horizontal lines between those phases of matter? Well, those are going to be your phase changes. So segment B to C, that represents solid to liquid, or the transition from a solid to a liquid, which is melting. And then D to E shows the transition of a liquid to a gas, which is evaporation or vaporization. Okay, notice that during these phase changes, the average kinetic energy or the temperature is staying the same. Okay, it's staying constant. So the temperature at which this substance is melting, so for segment BC, this could be considered the melting point, or I'm just going to write NP. And then the temperature at which this DE segment is staying the same represents the boiling point, or BP, right? Or the temperature at which that substance boils. Now, each heating and cooling curve represents a specific type of substance. So for example, let's just say that this heating curve is for H2O or for water. So we know that the melting point of water is 0 degrees Celsius and the boiling point of water is 100 degrees Celsius. Okay, so let's look at the energy changes that occur throughout these different segments. So on all of the red segments where we have one phase of matter, for your heating curve, kinetic energy is going to be increasing. The kinetic energy is going to be increasing and the average kinetic energy is going to be increasing. So the amount of motion that these particles have in this substance is going to increase as we go from a solid to a liquid to a gas. Okay, the more motion they're going to have. Now, what about potential energy during these segments? So during this time, we say that potential energy is constant. Okay, so potential energy is going to stay constant while a substance is in the solid, liquid, or gas phase. and kinetic energy is going to increase. Now, for your horizontal or the blue segments where your average kinetic energy is not changing, now the kinetic energy is staying constant. Okay, so kinetic energy constant there. Oops. And also here. And the potential energy now is what's going to increase. Okay, so during the increasing red lines that represent either the substance being in either a solid, liquid, or gas phase, the kinetic energy is going to be increasing for a heating curve. The more heat energy that is being put into that substance, the greater the motion and the kinetic energy is going to be, and the greater the temperature. Okay, so that's why our kinetic energy is going to be increasing when our potential energy is going to be staying constant. Now, during these phase changes where it's a transition from one state to another, all of that energy that that substance is absorbing is not going to go into the temperature, into increasing the temperature, but rather it's going to be used for these particles to overcome the intermolecular forces, the forces that are between their molecules. It's going to be used to kind of get them further apart from each other and start to rip away from each other more, and to create more space between those particles. So that's why for these phase change segments, the blue ones, your potential energy is what's going to be increasing. Okay. So now let's look at the opposite for a cooling curve. So this is going to represent more exothermic processes. So heat energy is going to be released. Okay, so again, you have your time on the x-axis and you have temperature on the y-axis. So this first segment, AB, is going to represent a gas now. Okay, the greater the average kinetic energy, the further away those particles are going to be, or rather, how fast or how much motion those particles are going to have. So now we're going to go from a gas to a liquid, ending with a solid. So almost like the reverse of your heating curve. Okay, we can draw these particles kind of further apart. And then as that temperature is decreasing, those intermolecular forces are getting stronger and those particles are becoming more and more compact. Okay, so these are going to be, it's going to be pretty much the opposite of your heating curve. So as you decrease down this cooling curve or this downwards facing staircase, your kinetic energy is going to be decreasing, and potential energy is going to be constant while that substance is in all of these states. Okay, and again, these horizontal lines where temperature is not changing, where kinetic energy is constant, okay, these are going to represent the actual phase changes, the transitions from one state to the next. So from a gas to a liquid, that's condensation. And from a liquid to a solid, that's freezing or solidification. Okay, and at these phase transitions, condensation, and freezing, your potential energy is going to be decreasing. Okay, and that potential energy is decreasing now as you go from a gas to a liquid to solid because these intermolecular forces between particles are essentially getting stronger. These particles are having a stronger force of attraction, making them get closer and closer and closer to one another. So, therefore, their potential energy is going to be decreasing. Okay, and similarly to the last one, okay, these phase changes of condensation and freezing are representing the temperature at which that they occur. So from gas to a liquid, this condensation, this temperature is the same thing as the boiling point, right? It's just in reverse. Okay, maybe we can even call it the condensation point. And then this one could be the freezing point, okay, which is the same thing as the melting point, right? The temperature at which this substance will freeze. Okay, so the most important things to remember about these two is to understand the differences between a sloped line like this and a horizontal line like this. Okay, the lines with the slopes are going to represent the actual phase of matter. So whether that be a solid, a liquid, or a gas. And these horizontal lines where your average kinetic energy or your temperature is constant and staying the same represents that some sort of phase change. Okay, and depending on if you have a heating or a cooling curve, for your heating curve during these while you're at a certain state of matter, that kinetic energy is going to be increasing while your potential energy is staying constant. This is for heating. Now, if you had a cooling curve and you had a decreasing line, that's when your kinetic energy and your average kinetic energy are going to be decreasing. Okay, the temperature is dropping, but our potential energy is staying the same. And only when you are going through some sort of transition from one phase to the next, or this phase change, that is when your kinetic energy is constant. Okay, because all of that heat being absorbed is going into changing the potential energy. Okay, whether that be increasing with the heating curve or decreasing with your cooling curve. Okay, so definitely make sure you practice all of these and you keep studying. I would like you now to go look at the practice questions, multiple choice questions on pages 10 and 11 for 8.6. Okay, so you can start looking at questions that are related to these curves.